So we're going to talk more about rotation. So before we get started, this thing has lost me. I think it's following me. Is it following me? Yes. Okay. So I was going to do this demonstration, but we had a bunch of technical difficulties last time. So let's say I have this bicycle wheel and I have this string. What happens if I let go of the bicycle wheel? It's gonna fall. All right, perfect. Now I'm going to give it some angular momentum. Okay, how do we give it angular momentum? I'm going to need help with this actually. I'm going to choose you because you're right here. Can you spin this as fast as you can? That's just a lot easier. Okay. Faster. Okay, that's good. Okay, now I'm going to grab the string and let go. What's going to happen? Okay, doesn't fall. All right. So when I say that angular momentum is a vector, this is what I mean. Okay, when this thing is spinning, there's a vector that points this way. Okay, so it actually has a feature, and this is a little bit of gyroscopic motion, which we might get a chance to go over depending on how much time we have. But yeah, we'll also do some fun demonstrations with this cool rotating platform, and hopefully I won't sprain my ankle, or unless anybody else wants to volunteer to sprain their ankle. It's okay. I have strong ankles. Okay. So let's talk about more rotation. We've talked a little bit about rotational kinetic energy. Okay. And we can use that in conservation of energy. Remember, if something is rotating or spinning, it has rotational kinetic energy. If it's moving in a linear fashion, it has translational kinetic energy. That's 1/2 mv squared. If it's rotating, that's 1/2 I omega squared. Okay. And if it's doing both, then you use both. So whenever something's moving, you just have to think, how is it moving? All right. There's also vibrational kinetic energy, and we don't deal with that until thermodynamics, but that's pretty much all the kinds. So let's talk about more dynamics of rotational motion. So more spinning things. We've talked about the rotational equivalent of, okay, let's start. The rotational equivalent of position, like X position. What is that? We'll start with the first one. You go from X to theta, right? So you measure things in a line, or you measure things on a circle with radians, okay? How about velocity? What's the rotational version of velocity? Omega, which is angular velocity. How about acceleration? What's the rotational version of acceleration? Alpha, which is angular acceleration, okay? We talked about the rotational equivalent of mass. What's the rotational equivalent of mass? Well, mass is inertia. What's the thing we have to do integrals for? Moment of inertia. So remember, if you're just moving linearly, you only care about the mass, right? But if you're turning, you have to care about your moment of inertia, because remember, it's easier to spin like this than it is to spin like this, okay? So we'll talk more about that in terms of momentum in a minute. Well, in several minutes. And so we haven't talked about the rotational equivalent of force, and that's going to be torque, okay? And torque is a topic that I think a lot of people find tricky at first, but it's an important topic, especially if you're like, I don't know, like a mechanical engineer. There's like a whole class on just torque. Actually, I think there's 2 classes on torque. They're called like statics and dynamics. It's a lot of torque in there, okay? So we have torque. We'll talk about torque and angular acceleration, because remember, F equals ma. Well, that means that there's probably an equivalent version of that for rotation, where you replace force with the thing for force, which is torque. And then you replace mass with the rotational thing for mass, which is moment of inertia. And then you replace acceleration with the rotational acceleration, which is angular acceleration. So that's what we're going to talk about there. We'll talk about rigid body rotation about an axis. Okay. We'll talk about work and power now that we're basically just going back through all of the things we did for linear stuff. So work and power. Then we'll talk about angular momentum. So momentum for things that are rotating. And then we'll talk about conservation of angular momentum, including rotation. So we're going back through all of the things we did for linear motion, and we're adding in the ability to rotate. Okay. So we're going to start with torque. And torque is tricky for people mostly because it's a cross product, okay? And cross products are like the trickiest of the vector multiplications because they're not super intuitive right away. So let's say you have this wrench. Where would you say the axis of rotation is for this? You have this little bolt nut combination, okay? So if you apply a force to the handle over here, that you know you're going to have a motion that looks like this, okay? But the key thing here is we're going to define something called the pivot point. It's sometimes also called the axis of rotation, but it's just the point around which the object rotates, okay? So it's the rotational center. And then we're also going to have this point where the force is applied, okay? So between those 2 points, we have a vector we're going to call R. It could be X, Y, Z, it doesn't matter, but it's just a distance between the pivot point and the torque, okay? And there's an angle between the force and this length that we call theta, but for some reason here I've decided to call it phi. I don't know why. So it doesn't matter, it's just an angle. So we know that torque is going to be FR sine phi, but really the definition is torque is the force crossed with R, okay? Where R is defined as the distance between the rotational point and where the force acts. All right. Now, which way is the positive torque? Which turning direction? Counterclockwise. Remember, counterclockwise is positive, right? Clockwise is negative. So that's the standard. Obviously, you can remember when we make our own coordinate systems, we can change that, but just this is the default setting for positive and negative, okay? And the horrifying units of torque, remember the units were really nice in the first few chapters and they've gotten uglier and uglier as we've gone on. The units for torque are Newton meters. Now you remember when we did work, if you multiply a Newton by a meter, it gave you a joule, but it doesn't now because vectors, okay? Yeah, so yes. It should be, is it not on modules?
You go 9.
Okay, can you give me a second? Let me just finish this section and then I'll post it. Okay, so remember, torque is the rotational equivalent of force, okay? The rotational equivalent of force. And that means that anytime we have force, we can use torque. So we're gonna try a clicker question. And remember, cross product, more perpendicular is bigger. All right, we have mostly A, which is great because A is the answer. But just to go through these, make sure this is following me. Okay. Torque here. Let's say this length is, let's just say call it 1 meter for the sake of it, right? So that's going to be 2 Newtons times 1 meter, that's 2 Newton meters, okay? Torque here. 2 times 1/2, so that should be 1 Newton meter, so that's smaller. What's the torque here? Smaller, real small. 0, right? Why is it 0? It's a cross product, right? And I mean, if you need an example of what this would be like, so let's say this is our like thing that we're like our stick thing that's there. If I pull here with 2 Newtons, right? Or if I push here with 2 Newtons, okay, that's going to be more torque than if I push in the middle of the door. If I just pull the door this way, it's not going to open or close. Okay, so that's the example that's happening in part C. And then this one is 4 Newtons times 1/2, so it should be 2 Newton meters, which should be the same as A. So that's A and D being the same, they're the largest. B is the second largest because you're pushing in the middle. And then C is going to be 0 because it's a cross product. So if the angle between your 2 vectors is 0 or 180, it gives you 0 torque. Okay, cool. So that's A. Okay. So I'm going to go over this. Bear with me while I try to draw a meter stick again. It's never gone well. in the history of drawing this meter stick. Oh, yay, finally. All right. Make it look, oh no, you look like a meter stick. Okay, so let's just label the numbers. Let's say 0 and 100, and then there should be 50 in the middle. So 10, 20, 30, 40, 50, 60, 70, 80, 90. Not perfect, but you get the general idea. So we have a meter stick. The meter stick has a mass of 150 grams. It has a 1 kilogram mass hanging at the 20 centimeter mark, and then a 0.25 kilogram mass hanging at the 80 centimeter mark. And then the meter stick is suspended by a string located at the 30 centimeter mark. So we're going to first put the string here. And why do we care about where the string is located? What would we call that position? It's the pivot point, and it's also our 0. Okay, so we're going to measure everything from the pivot point, because remember, the R in torque is the distance from the axis of rotation or pivot point to where the force acts. Okay, the next thing we need to do is establish where our forces are. So we have 2 masses hanging, and they happen to be at 20 centimeters and at 80 centimeters. But we also know that the meter stick has a mass. So where does the meter stick's mass act? At the center of mass. And where is the center of mass? 50, right? So that's going to be right here. Okay, just hang on. I just have to think. Oh, cool. It stopped recording for no apparent reason. Is it recording? Hang on. Just give me a second. I don't know why my computer hates me. Okay, now it's recording. Cool. So, bless you. So we have these 3 different forces, and the way that we're going to calculate these forces is this is going to be M1G. We'll call this M2G, and this will be mass, center of mass G. Okay. This one, this first one is 1 kilogram, right? So M1 is 1 kilogram. This is 0.25 kilograms, and then this is 0.150 kilograms. Okay, just for. Where were you looking? Okay. I take everything back. Sorry. Well, I'm glad we've all figured that out. So we just want to calculate the torque, but we have to know one other thing. So what are the distances, right? What are our R's? So what's this distance? Yeah, so this is R1. We'll call that 10 centimeters. Then we have this distance, which we'll call R, center of mass. What's that going to be? 20 centimeters. And then last but not least, we have this distance. And this is R2, which we'll call 50 centimeters. And of course, these are going to need to be in meters. I'll convert them when we do the math. So in order to calculate torque, we know that torque is equal to F cross R. Okay, we have our forces and we have our R's. Then we also know that that means that it's FR sine theta, and just don't forget about the signs. Okay, the signs will come from the cross product, but we'll talk about how we get them in a more simple way. What do we know about the angles here? What are the angles between R and F in all of these cases? 90-degree angles. So that means because theta is 90, we always have sine of 90. And what is sine of 90? 1. Okay. So that means we just have to calculate our 3 torques, and then we'll add them together. So in order to get our final answer, we're just taking the sum of all of our torques, but let's just calculate torque 1. That's going to be M1 times G times R1. Okay, sine of 90, which is 1. So sine of 90, which is 1. Okay. So we say 1 kilogram, 9.8 meters per second squared, and then 0.1 meters. That's going to give us a torque of 0.98. And is that going to be positive or negative?
Positive.
Okay, so think about this, okay? Here's our pivot point. If we have a force pointing this way, is this going to rotate clockwise or counterclockwise? Counterclockwise, right? It's going to cause the meter stick to rotate this way, okay? So because it's going to rotate this way, that means that counterclockwise is a positive torque, so this is going to be positive, okay? Torque 2.
Are you putting negative 10 or regular 10? I can't see.
Just regular, wait, 10?
Second.
Oh, it's a horrible 0. Okay, fine. It's better now. I'm gonna start grading you guys on your penmanship. Okay. Just out of spite. No, I won't. Okay, so M2G, that's our force, okay, times our distance, R2, times sine of theta, which is 1, okay, so, well, sine of 90, which is 1. We plug these in, that's going to be 0.25 kilograms times 9.8 meters per second squared, times 0.5 meters, that's 50 centimeters. That's going to give us, why is it like that? Okay, 1.23 Newton meters. Is that positive or negative this time? It's negative. Okay. And then last but not least, we have T, center of mass. That's going to be mass of the center of mass of the meter stick, G times R, center of mass. That's going to give us 0.15 kilograms times 9.8 times 0.2. I'm leaving out the units because you get the idea, and also because I'm out of space. And then if you add all these up, that's going to give us negative 0.294 Newton meters. Okay, it's negative because, once again, it would cause the meter stick to rotate clockwise. So that's how we get our signs. All right. Now we want the total mass, or the total torque or the net torque. So that means we add up all of our torques. Okay, so that's going to be 0.98 Newton meters minus 1.23 Newton meters minus 0.294 Newton meters, and that gives us negative 0.54 Newton meters. Okay, which probably doesn't mean a whole lot to you in a physical sense, but that's our answer. So now we have a torque. Okay, now we're doing this because if you have a torque and we knew the moment of inertia for the meter stick, you could calculate the angular acceleration. Okay, so that's where we're heading with this. We could just use torque equals moment of inertia times angular acceleration, and we could see how fast this thing is rotating. And then once you have angular acceleration, you can do kinematics. Okay, so it's really just F equals ma, but slightly more complicated, because every time you have a force, you also have to know where the force is and then calculate the torque.
So you can use this for like a catapult or something?
Yeah, you could. Yeah. So if you wanted to, calculate how fast something would go at the end of like the motion of a catapult, you could calculate the torque on the catapult. You could calculate the moment of inertia of the arm of the catapult, and then you could find the angular acceleration, and you can use that to find the final speed, right? So definitely something you could use for that. Okay. Any questions on this?